Today's screencast is for a packed column distillation, and we have a bunch of information given to us here. I'll let you read through the problem, and I will start writing. So we have a column that has a feed of 50 mole per hour, and it's a saturated liquid, and Z equals 0.5. We are told that it's a total condenser and a partial reboiler, and we know what our distillate composition is. The desired one is 0.95, and the desired bottoms are 0.05. We have a certain packing. It's run at a reflux ratio that's 1.5 times the minimum. So L over D equals 1.5 L over D min. And we know that Hg is 1.3, given that down here. And we are also given Kxa over Kya values in the stripping and enriching sections. And what we're looking for is the height of the column using the HTU-NTU graphical method. Let's review what this method utilizes. So the first step is to determine NG, or the NTUs. And so first we will plot the top and bottom operating lines. Then we'll determine the limits of integration from these lines. Step C is we will pick points on the top and the bottom operating lines to determine Xi, Yi. We'll calculate 1 over Yi minus Y for each set of points. Then we'll plot 1 over Yi minus Y versus Y. And finally we will calculate the areas under these curves to plug that into our height equation in step 2, with the height equaling Hg Ng enriching plus Hg Ng stripping. So I want to point out something, that often Hg in enriching and Hg in stripping are not the same, but for us they are the same. V equals V bar, and this is because the feed is a saturated liquid, and for this type of feed, V equals V bar. So our Hg's values are going to be the same in the enriching and the stripping sections. Well, let's start the problem. Part A, plot the top and bottom operating lines. So, by the way, I'm just going to go through each of the steps that we have just gone through right here on this slide. So we'll start with 1A, which is plotting the top and bottom operating lines. So what is L over D? We need to find it from the minimum L over D that we use with the pinch point. So first we need to figure out what kind of feed we have. Feed is a saturated liquid, so it's going to be a horizontal line at the point Z, Z. So the feed line will just look like this. So this is the feed line. Now this is a standard distillation column, so we can use the point XD, XD for the top operating point, top operating line. So that's here. And the pinch point, let me use my ruler. The pinch point will be here. And so this will be a slope of L over V min. And if you don't understand why we're doing that, look at the screencast for distillation reflux, how we determine minimum reflux. So L over V min equals 0.95 minus 0.84 over 0.95 minus 0.5. So this is this point here. That equals 0.24. Now L over V min equals L over D min over L over D min plus 1. So that equals 0.24, and L over D min equals 0.316. So our L over D value, L over D equals 1.3 L over D min equals 0.474, and L over V equals L over D plus 1 equals 0.322. So our top operating line is y equals 0.322 x plus 0.644. This value is just the y-intercept of xd over L over d plus 1. That equals 0.644. So let's plot this top operating line. The y-intercept is 0.644. And plot this. And then we will plot the bottom operating line. It goes through xb, xb. And the intersection of the top operating line and the feed looks like that. And let's go to the next page where we have this already plotted. This is our top operating line, and this is our bottom operating line. So our limits of integration, y out enriching equals 0.95. So that's up here. Y in enriching equals y out stripping equals 0.802 here, and then y in stripping equals, because it's a partial reboiler, 0.15. Because for a partial reboiler we have x out which is xb, is in equilibrium with the vapor coming off of the partial reboiler. So we go up here to get 0.15, and then the 0.802 was right here, and the 0.95 was right here. Now we're going to move on to part C. Pick points on the top and bottom operating lines xy and determine xi, yi. And so I'll just pick random points. Start here. My equation for this is yi equals negative kxa over kya xi plus kxa over kya x plus y. So I pick a point on my operating line and I plug in the values for x and y, and then I've got that point, and then I usually just plug in a value of 0 for x, and then I calculate what yi is. So I get that point, and then I plot that in Excel, and I'll get something like this, and I continue and do that for all these different points. I just plug in different values of x and y, then I just get another point with which to plot the line. So I make xi equal to 0 so that I can determine what yi is, and then I plot that line. It goes way up, and it'll look like this. And then for the bottoms, I do the same thing, and I start here, and I'll get lines that are more like this in the bottoms. And for each one of these, I find out what the intersection is with the equilibrium data, and that's my value of xi, yi. So I've done this on the next page. So for these first values, let's see, x equals 0.11. So I started with that, and I found out what y was based on the bottom operating line, y equals 0.15. Then I plotted my line using the equation that we have on the other page, and I'll write again here, y equals negative kxa over kya xi plus kxa kya x plus y. So I plot my line, and then I see where it intersects with the equilibrium data, and here we've got xi equals 0.75 and yi equals 0.24. I do that for the next point, 0.2. I've got 0.2, and the corresponding y is 0.3. So I put that 0.3 here. I draw my line, and I see where it intersects the equilibrium data. And so xi equals 0.15 and xy equals 0.54. Oops, I think that's supposed to be 4.5. And then we do it also for here. So that's going to be the 0.3 here. And we do it up until we get to the intersection of the bottom and the top operating line. And at that point, we switch to the slope of the top operating line. So We have values of negative kxa over kya for the stripping and enriching sections. And those were given here. So we have a stripping slope, and we've got a slope for the enriching section. Note that they are different. So after I've tabulated all of these values and I calculate 1 over yi minus y for each, then I plot 1 over yi minus y over y. And I get this plot as seen here. Now I want to determine what the area is under this plot. So we need to determine our limits of integration. We've got that is the bottom's going into the stripping, and then we switch from the stripping to the enriching at 0.8, and then the output from the enriching section is 0.95, 0.8, and 0.15. So this section is the stripping, and this section is enriching. To determine the area under this, I used the trapezoidal rule, and I used a whole bunch of areas. And I had area 1, area 2, area 3, area 4, area 5, area 6. And let me show you how I got the area in each one of these. So for the trapezoidal rule, you could also use Simpson's rule. The area equals h times b1 plus b2 over 2. So for instance, for area 1, I have the height equals 0.35 minus 0.15, and that equals 0.2. B1 equals 11. We'll go across here, we get 11. B2 equals 4. So A1 equals 1.5. Let's do one other area. We'll do area 2. The height equals 0.72 minus 0.35. So this is 0.72. That equals 0.37. B1 equals 4. B2 equals 18. So this is approximately 18. And A2 equals 4.07. So I did this for each of these areas and got A enriching equal to 6.01, and this equals NG enriching, and A in stripping. This is the area under the curve. So this is the area under the 1 over yi minus y curve. So A in the stripping equals 7.57 equals NG in the stripping. Finally, we will calculate the overall height. The height equals 1.3, which is our HG that was given to us at the beginning in the problem statement. HG 1.3 feet times 6.01 plus 1.3 feet times 7.57. And so the overall height equals 17.7 feet. That is the total height required for this column.